So, did anyone try this thing? Did you guys even remember there was a homework problem? Forgot. Okay, so how do we do this? Okay, let's see. Let's find the ratio, okay, V naught by VA. That would be a pretty good means question, actually. Let's start from there, then we will see V naught. So, let me show you one, and then I'll ask you one more. So, we have the square plate. This is O, and this is A. Everywhere there is a positive charge in sigma. Now, tell me one thing. The potential formula, right, is kq by a normally. That means no matter what kind of object you take, because the dimensions have to match, the potential will be proportional to q by a. Agree with this? Think about this. Till now, every question we did, when I said what is the potential here, you got the same thing here. So when you had a lot of charges, look at this thing. The potential is k lambda, lambda is q by d. Right? When you had a lot of charges, k q by d, potential here kq by a. So simple thing, dimensional analysis, the potential, whatever is this, it must be always proportional to the charge on the body by the side A, because these are the only two dimensions you have. That constant can be anything. And what is q? Q is nothing but sigma into a square by a. So this is proportional to a. Again, we are talking about the center. Is this making sense? Since the potential formula for a point charge is kq by a, by dimensional analysis, we can say, right, the potential at the center must be proportional to the charge on the square plate by side of the square plate, because that's how the dimensions will match. Now, if you take a bigger square plate of side 2A, this A here becomes the center of this big square plate now. Making sense? Because this thing is made of 4 small square plates. So the A was the corner for the small plate. But when you take 3 more plates, now suddenly it becomes the center of the big plate. Is that making sense? So the velocity here, potential at the center here. So VA for the big plate must be proportional to 2A. Therefore, VA for the big plate must be equal to V naught. So V naught is the potential for that small plate, 2V naught. Is that making sense? So if you take a square plate of side A and 2A, the center of the potential will double. But this big plate is nothing but 4 times VA of the small plates. Because the potential at this A is because of plate 1, plate 2, plate 3, plate 4. That means the VA due to that small plate is V naught by 2. That means this ratio here, which we got, V naught by VA, the ratio will be 2:1. So no integration, nothing. Just by symmetry, you can figure out this much ratio. Is the logic making sense? By dimensions, we know it should be proportional to Q by A. Now that constant could be anything. So if you take a square plate, again at the center only, because center is symmetrical. If you take the center, I can confidently say it should depend on the charge of the square plate. It should depend on the side of the square plate. Now, if you make a big square plate of side 2A, the potential will become 2A, 2V naught. But that big square plate ka center is nothing but A for the small square plate. And there are 4 small square plates, and each one will contribute 1/4 of the voltage. So total is 2V naught. Uska 1/4 is V naught by 2. All sure of this? Any doubts on this? These are the kind of questions you'll get in mains. Not tough, but you have to think. What is the value? We will do that. Now, using this logic, can you guys find for this? What if I give you a cube? O is the center, A is the vertex. Uniformly charged cube. Find the ratio of potential at the center by potential at the corner. There, you try this time. I'll give you a minute or two. You got the idea how to handle these things. Symmetrical. You give me any other random point or any other shape, we couldn't handle this. area. Solve. Why are you guessing? Today your CNS ka bits have started. One person got 327, one person got 319, 298, 269, 250, 230, 175. Yeah, we have all scores. How do we do what was the logic? Again, same story. The potential must depend on charge by side. You take a cube, you take a parabola, you take any stupid shape, you take an amoeba also, you can confidently say the potential at any point is proportional to charge by simply units and dimensions. There is no other option there. You cannot get a q square or a square. What changes is this proportionality constant ka thing will change. Nahi Utsa, that is wrong. Are you sure? I'll get a -1. Final is. Think for another 30-40 seconds and get it. I don't want to give a -1 randomly. Nahi Utsa. Samyak. Okay. Samyak got it. Arya also got it. Let's see. Again, what is the story there? Same thing. So the potential at the center of the small cube, so VO, is proportional to Q by A. Q is nothing but rho into A cube by A. So this is proportional to A square. Now, if you take a big cube, to A, the A becomes the center of the big cube. So VA, that is the center of the big cube. So VA for the big cube is proportional to 2A ka whole square. That is 4A square. That means potential at the center of the big cube. So if you make the cube ka size double, that must be 4 times V naught. But this big cube is made of 8 small cubes. So that will be 8 into VA small cubes. Right? To make a big cube, you need 8 small cubes. So we get VA by V naught is 1 by 2 or 2:1. Same answer you get. Clear with this? You get the same answer as a square plate. It just works out. Any doubts on this? Did you see? No calculations, no integration, nothing. So this is a pretty good question. These are really good questions at a mains level. Any doubts on this? How we got this thing? Now, how to actually calculate the value? If you see, we did this kind of a technique in moment of inertia of an equilateral triangle. Yeah, we divided the big equilateral triangle into 4 small equilateral triangles, and we used parallaxes theorem, and we got it. So, how to find for the square? Now, see. Now, for a square plate, I will just take this one sector, one piece. I'll just exaggerate the figure. So this distance is a by 2. From here, take a very thin slice. like this. Now this is so small, so this angle is alpha, this angle is d alpha. It is so small, I can treat this like a sector. That's the whole idea, that you have to treat it like a sector. So treat it like a small sector there. Then if you take this as radius r, so now you have created a very thin sector whose angle is d alpha, and the radius r will be how much? That will be cos na r by a by 2 sec alpha. Now for a sector, we know the potential. So V due to a sector, what was the formula we derived? Kr sigma r, no, K sigma theta r, K sigma theta will be d alpha, and that is smaller. So that would be K sigma a by 2 sec alpha d alpha. And if you look at the limits of alpha, if here alpha is 0, here alpha is 45. So the potential at the center due to this 1/8 of a plate is K sigma a by 2 integral sec alpha d alpha. Limits will go from 0 to pi by 4. And in case you don't know sec alpha integration, I gave you this. That's ln sec theta plus tan theta. That would be K sigma a by 2 ln sec alpha plus tan alpha. Limits will go from 0 to pi by 4. When you keep pi by 4, you'll get root 2 plus 1. When you keep 0, you'll get ln 1. That's 0 anyway. So you will end up with K sigma a by 2 ln root 2 plus 1. But remember, this is only due to 1/8 of a plate. So potential at the center due to the entire square will be 8 times K sigma a by 2 ln root 2 plus 1. That's 4. K is 1 by 4 pi epsilon. Sigma a by 2 ln root 2 plus 1. So 2, 4, that goes off sigma a by pi epsilon ln root 2 plus 1. Yeah, it's a little difficult to get the idea that you can take a sector for a triangle. But now you know the technique. Next time when you see, you'll be able to handle this. Some other method I couldn't figure out so far. This is the only thing that clicked to me also. And this thing I found it useful, but it looks easy. That is because you already know the sector ka formula. But if you don't know the sector, then this thing is not easy, right? You have to figure out from there. Rods are not a good idea. If you remember, when I asked you to calculate the field for a rod, did you notice I didn't ask you to find potential here? And that is because that value itself will come in ln. It's not a good value. अभी ln का वापस integrate करना पड़ेगा. That will be even more messed up. It's not like we can't do. Mathematically, it just becomes too intense for us. So we just don't do it. Clever this, but yeah, this thing still looks decent. All clear this. Yeah. So now since I know V naught, I can get VA from this logic, isn't it? V naught by VA is 2 is to 1. So VA आ जाएगा यहाँ से. So there's no need to integrate for VA separately now. All clear with this? Next thing. That's one good question there. Field on the action line of a ring. So we got a ring here, plus Q, radius R. So this is the axial line. So axial line, right? Axial line nahi hai. Axial meaning the line passing through the center and perpendicular to the plane, right? So if you choose a point P somewhere here, we want to find the field here. So let the distance be X. Everyone able to visualize how is the line? Meaning if I draw another view, the view will look like this. See? This is the axial line. So which you're getting at the line perpendicular to the plane and passing through the center. So this is the another view of it. So if you take a small point here, dq, this angle will be theta, this will be theta. So this will give you field at dE. So the field at point P will be integral dE cos theta. The field is nothing but k dq. The distance is, the radius is r, and that is x. So r square plus x square ka root ka whole square, and cos theta would be this thing. Now, if you observe here, everything is concept except dq. So this will be k r square plus x square, and cos theta would be x by root over r square plus x square integral dq. Integral dq is the total charge. So the formula comes out to be k q x. You should definitely mug up this. Standard result. So this is the field on the axial line, EP. Similarly, you can do the same thing for potential. Potential is more easy. It is a scalar quantity, so kq by root over r square plus x square. And if you plot the value of field for E versus x graph, you can clearly see when x is 0, field is 0, so the value will rise and then drops to 0 at infinity. The value will rise and go to 0 at the negative value. It will reach a peak value at r by root 2. We can do maximum minima and you can get it from there. So the value will reach maximum at r by root 2 and minus r by root 2. And this thing I did teach you before in calculus. When I taught you maximum minima, we did this kind of stuff. There. Look at this function, yeah? Kqx by x square plus a square whole power 3 by 2. That looks something like this. Anyway, so there, these are the important formulas there. You should definitely remember in the graph, and you should know this thing at x is equal to plus or minus r by root 2, the value will be maximum. That's a standard question actually. Comes in exams like CET or means or bits. Clear with this? Great. Let's see a question on this. So we have a ring plus q, radius r. The ring is fixed charged ring. Gravity is present. You kept a charge q plus q and mass m at a distance x from the axis, and it is at rest. So the repulsion between the ring and the point particle is being balanced by the weight. Find x if the particle is in stable equilibrium. So if I ask you this question, right, find x if it is in equilibrium, then what will be the answer? And if I say find a stable equilibrium, the whole game changes. So a simple mains question would be this: at how many points can I keep it at rest? That would be a mains question. Find the stable equilibrium. That will still become a decent advanced question. How can you get infinity? तो ना कुछ भी बोलते हो infinity. You're saying there are infinite points I can keep it at rest. Get it straightforward, right? EQ, the repulsion force must be equal to mg. So that is how you get the equilibrium. But what is this word stable equilibrium? Like, think. I'll give you a minute or two. Why people are absent today? नहीं रे, won't get 6 points. सिर्फ 2 पॉइंट आएगा रे. नहीं रहा देते. Why are we Ruttu so special about it? There is a particular value of mg. See, why should there be a maximum field to balance mg? Okay, let's see. At x less than x root 2. What is that, right? What's that? Just think about the way you type the answer. X less than x square root 2. What does it even mean? Now, first thing, let's try to understand here. So it's a straightforward equilibrium problem. So there is a force mg which is trying to pull it down, and there's a repulsion force eq which is trying to balance up. So we get eq is equal to mg. Yeah, and E is nothing but kqx by x square plus r square whole power 3 by 2 into q is equal to mg. Right? If you send it that side and square it and do all this, you can clearly notice something. Just look at the graph, you'll understand. When you plotted E versus X graph, except the peak value, forget about the left side, we are only talking about the repulsion. Except the peak value, so whatever is this value that you're getting, let's say E, this will occur at two positions, isn't it? X1 and X2. In a rare case, you will get it at the maxima, so that is fine. But generally, you'll end up with two answers here. So when you solve this, you'll end up with x1 and x2. So there are 2 points where you can keep it at rest. But among them, there's only one point which is a stable equilibrium. So the maxima will occur at r by root 2. So the question is, what is my answer? Is it x1 or x2? So you'll get one answer greater than r by root 2, one answer less than r by root 2. Everyone got it? Why there'll be two answers? Because the value increases and decreases. There are 2 points where that EQ will balance mg, but one is stable and one is unstable. Now, think about this. Again, how do we define something is stable and unstable? Disturb it. If it comes back, it is stable. If it doesn't come back, it is unstable. So let's check the scenario. So let's say this is the point where x is equal to r by root 2. This is the point where E is maximum. Let's say your point is here, meaning somewhere here you got balance. So let's say this is x1. So we are taking the case where x1 is less than r by root 2. Now look at the forces here. This is mg and this is EQ. Now, if I push it upward, what will happen? Now remember, as you go up, the field is increasing. If we push it up, E increases because you're going towards the maximum point. Therefore, EQ becomes greater than mg. Means it will keep going up. This is not stable. If you disturb and if it keeps going in the, it will keep going up. This is an unstable equilibrium. Same thing, if I push it down, E will decrease, mg becomes greater than EQ, it will keep coming down. Understood how to check? So simple test, push it and see, is it coming back or going away? Let's take the other case, where x is greater than r by root 2. So this is your x2. So this is the point where you have x is equal to r by root 2. And let's say your point is occurring here. So this is your mg and this is your EQ. Same story. If you push it down or push it up, if pushed up, E decreases, meaning mg becomes greater than EQ. It comes down. This is stable equilibrium. And if it is in stable equilibrium, you know, right? I can ask you find the time period for small oscillations. So you can play all that games you want, but I hope you got the point. So the one which is greater than r by root 2 is your answer. Even though you get two roots, you have to be careful which one to choose. All clear with this? There. So we are playing with equilibrium and this thing. So this is what I was saying. Even though we say chapter is electrostatics, you will get some results from there. And after that, the whole thing is based on mechanics. Next one. Any doubts on this? Great. Let's see one more. We got a ring here, plus Q, radius R. We got another ring here, plus Q, radius R, identical rings. Let's say the distance between them is 2R root 3. So from here, we have projected a particle of charge minus Q and mass M. Let's call this A and let's call this B. So it is projected along the axis. The charge minus QM is projected along the axis from A to B. Find the U minimum. What is the minimum speed required to reach point B? Hmm. What is the catch? Did you get 0? I'll tell you a story. See. So, whenever you launch a rocket, let's say from Earth to Moon, so let's say you're sending a missile to on Moon and you just want to blast it, getting it. So we don't want to land. So normally, right, when you launch a rocket also, na, this is what happens to the rocket. See. So initially, when it is going from the Earth, the rocket is like this. It's pointing towards the Moon and the engine is on. As the rocket goes, something happens. They turn the rocket like this, and then they go to the Moon. So why do you think they turn the rocket? The catch is this. As you're going away from the Earth, initially Earth's attraction is stronger. But at some point, the null point, at this point, the gravitational force due to the Earth and the gravitation due to the Moon, they become equal. So till this point, the rockets will be going against the Earth. After this point, the Moon ka force becomes stronger. So you have to reverse the rockets and slow down, and then you have to land. Now you tell me, if I really want to just land on the Moon, do I care that should I really go till the Moon? If I can launch something till the null point, and if you cross the null point, automatically Moon will pull you back, right? So if you want to go to the Moon, you need not go till the surface. You just need to reach the null point. Once you cross the null point, the Moon will automatically attract, and then you will fly off. Is that making sense? So once the rocket crosses the null point, the Moon will automatically pull the rocket. So there is no need to provide energy. So your final state is not the Moon, but the null point. So if you're launching a nuclear missile to destroy Moon, you just need to send it till the null point. So in these questions, that is the main thing. Because if you see by symmetry, A and B have same energy, it should be giving 0. In chemistry, right, you must have studied like this. The reactants have higher energy and the products have lower energy. Then why don't the reactants automatically become products? Because you have to provide something called an activation energy. Studied that. Even though your reactants are more stable, you need to provide activation energy for the reaction to proceed. So in this scenario, we can clearly see the midpoint is the null point, which is r by r root 3. So that means if your rocket can reach here, my job's done. So my null point is state 2. This is my state 1. If minus q reaches null point with a negligible velocity, so B is not your final state. It automatically goes to B. Because if you take A and B as your initial and final, the answer will get 0. That is the first thing. And second thing, some people do this mistake. You have to be careful. Now, be careful here. How to get the energy? So energy in state 1 is equal to energy in state 2. How do you write potential energy? Potential energy is charge into potential. Be careful. That is the formula now. So initially kinetic energy half mu square plus what is the potential at the center of the ring? Kq by r. That is due to your own ring plus kq by, there is another ring also, r square plus 2 root 3 r square into minus q. This is the potential due to A and that is the potential due to B. When you say potential at a point, it is due to everyone present in the space. Potential due to A and potential due to B. The second ring basically. Most people forget this. They take only one ring, so you have to be careful. So you have to find the potential due to both of them into minus q. That must be equal to state 2. The potential is kq by root over r square plus r root 3 whole square into minus q. Kinetic energy is 0. We have to do into 2 because there are two rings. So one of the common mistake, people forget to take the second ring, and so all this thing you'll end up with Yuga answer there. So these are the two things you have to be careful. You just need to reach the null point. Second, you need to get the potential at A and the null point due to both the rings. The total potential at the point into charge is the potential energy. I hope everyone is clear with that statement there. That is the definition of potential. Potential energy per unit charge. So potential energy is charge into potential. All clear with this? Any doubts on this? Clear, na Devansh? Clear? Vedika? Shreyansh? Shreyan? Great. Let's see the next one. We got a disk. Sigma and R. So it's a uniformly charged disk. This is point P and this is distance Z. Find the field at point P. Explain the result if R tends to infinity. Means if you make the radius of the disk infinity, then what do you think will happen? So first, let's get the field due to the disk. Think for a minute. If you couldn't figure out how to start, then I'll tell you. Then I'll give another minute or two. So how to take the elements? We have to take thin rings. So for all these rings, this will be axial line, isn't it? So you have to apply the axial line formula for the thin rings, and then you have to integrate all the rings. So start like this. Let the radius of the ring be x and let the thickness be dx. Start from there. Give it a try. Let's see. Continue doing. I'll show you the elements. So this is a disk. So we take a thin ring here of radius x and distance dx, thickness dx. So the charge on the ring will be sigma into the area, which is 2 pi x into dx. So because of this, we will get the field due to the ring. Remember the formula? K, Q ring, x is the distance from the ring, actually that is z, by r square, here r is x square, plus z square whole power 3 by 2. That is the field due to this ring at a distance z. And so if you want the net field at point P, we need to integrate this. Limits will go from 0 to r, k, z, sigma, 2 pi, x dx by x square plus z square. Here, remember, z is constant. We have to integrate this. Now, if you have done your integration, you would know what is this. But if you have not done, I taught you this. We use integration by substitution. So everyone focus on the class. Please stop talking and doing random stuff in the middle of the class. Please focus. You're in the class. So x square plus z square is equal to t square. So this is differentiate on both sides. This would be 2x dx. Z square is 0 and this is 2t dt. Right? And substitute there. That would be kz sigma 2 pi x dx becomes t dt. And the denominator becomes t square whole cube, t cube. K is 1 by 4 pi epsilon. So that will be sigma z by 2 epsilon. This would be minus 1 by t square. Right? And yeah, we'll put the limit there, 1 by t square. So that would be minus sigma z by 2 epsilon 1 by t square is x square plus z square. Limits will go from 0 to r. So if you solve this, you will end up with the field at point P will be sigma by 2 epsilon z. Put r there, 1 plus r square plus z square, and put 0 there. You'll get 1 by t thai actually. Root over x square plus z square. You get 1 by z minus 1 by root over r square plus z square. I'll show you a better way to remember this. Sigma by 2 epsilon 1 minus z by root over r square plus z square. This is the field. The easy way to remember is this way. So from the top of the disk, if you take till this point, and if you see this is the angle theta, what is cos theta? This is z. This is r. This is r square plus z square. So this can be written as sigma by 2 epsilon 1 minus cos theta. That's easy to remember, isn't it? The theta is the half angle. So instead of writing in terms of z and everything, that would be an easy formula to remember. So the field due to a disk is sigma by 2 epsilon 1 minus cos theta, where theta is the half angle. All clear with this? Please have a look at the elements. So it's more of a math there. And then the second part of the problem, what happens if your z is r is infinity? If you make r tending to infinity, then that term z by root over r square plus z square will tend to 0. You will get an interesting answer. You get field is equal to sigma by 2 epsilon. Basically, it becomes a constant. So what happened there? When you make a disk r infinity, it becomes a sheet. So if R tends to infinity, the disk gets converted to an infinite sheet. And for an infinite sheet, the field is constant. It doesn't matter how far you are, the field is always constant. So we get a second result there. So I'm just drawing it like a line, but it's an infinite sheet. So if you have an infinite sheet, sigma is the surface charge density. The field will be away from the sheet. So on the right side, it will be on the right, on the left side, it will be left. And the magnitude is sigma by 2 epsilon, independent of distance. No matter how far you go, the field will always remain constant. For negatives, it will be towards the sheet. And if you have minus sigma, then the field will be towards the sheet. Sigma by 2 epsilon and sigma by 2 epsilon. So there, so you can make a disk into an infinite sheet by making the radius infinity. So the field by a sheet by using rods. Yeah, you can do that. All clear with this? So the main thing was the integration, like how do we choose an element and how do we integrate? This is integration by substitution. If you have already done an integration in Max, this is pretty easy integration, like, right? So if your maximum if integration is done, you must have seen pretty deadly stuff. Is the uniform disk and the circular plate? Yeah, same thing. Utsa. Uniform disk, circular plate are the same thing. All clear with this? Now, how can they frame questions on this? You will get some easy ones. So once you know the infinite sheet, you can play around. They will say something like this. There is a large infinite sheet. Sigma, you also have gravity. We have a particle projected with u and theta. It is minus q and mass m. Find range. So this will fly and fall somewhere on the sheet. So we have a sheet sigma, and they will say there is a pendulum, mass m, charge q, length L, and gravity is present. Find time period. So indirectly, what they're asking, right? You know the value of E, then it is a standard stuff. So the sheet will simply give you the value of electric field. Once you know the electric field, EQ is the force. Then you know how to do G effective and all that stuff. Finish all this an easy one. These are like pretty straightforward means level questions. So the sheet ka job is simple. It will generate a constant field. And what will the field do? EQ is equal to force. And then it's all mechanics ka things. So
Sir, you will have to give a condition for B option.
what he can. I know you wonder you'll say something. I expected it. इतना मत सोच रहे मेंस में they'll not care about all that stuff. Exam में luckily there'll be 4 options, right? So you'll know. So what to do? I hope everyone understood what he was trying to say. फिर भी इसमें क्या कर सकते हैं पता है? If you say like that, they will simply say it is just connected to this point here. Then what will happen? It will be like this. It will oscillate here, na? You can just put a mod. You can play around if you want. But anyway, so it's pretty straightforward. So what are the forces on the particle here? So in this scenario, the particle will experience mg, the particle will experience force eq, and E is nothing but sigma by 2 epsilon. So from here we get G effective is G plus EQ by 2m, EQ by m. And then you know the range ka formula, U square sine 2 theta by 2 G effective. That's it. Okay, just get the G effective and you wrap it up there. Right? Same thing you will do here also. So this thing will be, tension will be mg plus EQ. This is equal to mg effective. We have done a few questions like this before. We get the time period will be 2 pi root over L by G effective, and you're done. Clear? So that infinite sheet will not do anything more than that. All clear with this? Next one. What if I have a hollow shell? Hollow hemisphere. Find the field at the center. Hollow hemisphere, sigma is the charge density. So this whole thing is plus. Radius r. Find the field at the center. So we have a uniformly charged hemisphere. Hollow hemisphere. Sigma is your surface charge density. O is your center. Find the electric field at the center of the hemisphere. You have to integrate a bit. And this is the, I think, third time you're seeing it. This is the fourth time you're seeing a hemisphere so far. First time we saw in center of mass, then we saw in moment of inertia, then we saw in fluid mechanics. And every time I keep telling you that only, how to integrate a hemisphere. The moment you see a hemisphere, you should know, अरे इसमें integration के element ऐसा होगा. That should click immediately. There. I hope you remember this thing. At an angle theta, take an RD theta. See, physics में, I'm telling you, there are like, sub मिला के, I think you'll get 10 to 12 models will be there. मतलब, standard integrations. If you know this much, you can handle everything in physics. They really won't go beyond this. So you should know, this shape integration will look like this. For a rod, it should look like this. For a solid sphere, it looks like this. The one that I taught you today, the square, that sector and all, that's actually really an exception. That's very rare. But this hemisphere is a very standard model. And it's fine if you forgot, but remember, okay, aisa hai, so go and revise, and end of the day, you have to remember that. People say, physics, you think a lot and all, but there are certain things you need to remember. You can think when you have some material in your head to think, right? You can't think in vacuum. Your juniors I'm taking, they're asking, sir, how will we get ideas? I said, if you do enough problems, you will get ideas from there after practicing 100 problems. If I give you a new problem, you'll have something to think and get an idea. You have no ideas, no problem solving, and you just want to suddenly figure it out. Either you're a Lord Buddha or you're some kind of a mad person. So isn't it? Think about it. And if you see the all the people in the world, right? There are only two type of people who are truly happy. One is Lord Buddha. One is a mad person. So in the class, sometimes people just keep laughing randomly in my class. So I tell them that only. Either you got enlightened or you have become mad. But obviously, right? Kids become enlightened. They never become mad. So I tell them that only. So you are that enlightened person. I leave the choice to them. Okay, let's see how will you take an element. So from here, at an angle theta, take a small angle d theta there. This is how we get a ring. I'll show it here. So the ring will look like this. I'm exaggerating it. So this would be your r d theta. And if you see the center here, isn't this the axial line? So this is theta. So this distance will be r sine theta. And the radius of the disk will be r cos theta. Perfect. So basically, this is your x, the distance on the axial line. This is your radius of the ring, that r. What is the charge on the ring? The charge on the ring will be 2 pi, the radius, which is r cos theta, into r d theta. Yeah. And then the field due to the ring will be k q ring, the distance x by r square plus x square whole power 3 by 2. This was the formula. So this would be 2 pi r square cos theta d theta, x is r sine theta. Denominator would be r square, so that would be r cube. In this scenario, limits will go from 0 to 90. And so that is the best part. So tomorrow, if someone asks you, right, not a full ring, but part of a sphere, you can change the limits. So r cube will go off. K will be 1 by, कुछ तो missing है, sigma is missing है. Sigma is also there. K is 1 by 4 pi epsilon, so that would be sigma by 2 epsilon integral sine theta cos theta d theta 0 to pi by 2. You can solve that. You'll end up with sigma by 4 epsilon. Yeah, right, Aditi. Well's got it. Clear with the integration? Right, Utsa, you got it. Okay, sigma pi, sigma is 1 by 4 pi epsilon. Yeah, I think some of you also got. Yeah, बोलो ना.
सर वो फील्ड का आपने कंपोनेंट नहीं दिया ना.
अरे रिंग का फील्ड तो एक्चुअली ऐसा ही होगा ना रे, किसका क्या
ओह
कंपोनेंट है?
सॉरी माय बैड.
तू भी ना.
दैट्स व्हाई माय इंटीग्रेशन वाज बैड.
Uh, तो उसका ऑलरेडी है कंपोनेंट और क्या. Now see, so if you take a hemisphere, it's a good result. Huh? This would be a good mains question. I have seen this question being asked in mains directly. So this is sigma to the field at the center. is sigma by 4 epsilon. Now, instead of this, let's say you only have part of a sphere. Right? Then your limits would be different. So I took theta from here. Let's say this is theta. So this will be 90 degrees. You took this is theta. So this is theta. And here theta is 0. Then when you integrate the same stuff, the limits would change from theta to 90. So क्या आएगा वो theta to 90? That would give you half minus something you will get. I think you get cos 2 theta types. You'll get sigma by 8 epsilon 1 minus cos 2 theta. If you put theta is equal to 0, I'm getting 0. You put sine 2 theta, I guess. Let's calculate it. Sigma by 2 epsilon, limits will go from theta to 90. This would be sine 2 theta by 2 d theta. So that would be sigma by 4 epsilon, and sine 2 theta ka integral will be one more 2 will come. So that will be sigma by 8 epsilon minus cos 2 theta 0 to 90 sigma by 8 epsilon. Cos 0 is 1 and theta tha ye. Cos 2 theta plus 1. Yeah, clear with this? If I put theta 0, I'll get sigma by 4 epsilon. If I put theta 90, I'll get 0. Perfect. I think that is the answer. Check it out. So if it is not a full sphere, this is how you do. All clear with this? So you can play around like this. Next time, we'll be doing hollow sphere and solid sphere. These are one of the most important shapes. We'll not be doing the derivations for them. We will do them in Gauss law later on. We'll see the proofs and results only. Take a break. Come back by 9:45. We'll continue from here. Any doubt so far? Sure. Come back by 9:45. uniformly charged hollow sphere or shell. Camps on everyone? I think you should write down the results with me. Take a paper, put on the results. You will need this. Should definitely mug up these results. Every time in mains, whenever they ask questions on electro or gravitation, 50% of the questions are on shell and solid sphere only. So if you have a shell of charge q plus q and radius r, the field is given by, the field inside is 0 for r less than r. R is nothing but distance from center. So spheres, right, are very interesting shapes. But outside, it behaves like a point charge at the center, k cube by r square for r greater than r. So basically, this is inside, this is outside. So that means if Earth was actually hollow and if someone throws you inside, you will just float inside. Right? And the graph for this will look like this. If you plot a graph between E versus R, it is 0, and then it would rise, and then it drops. So that 0 is pretty interesting. You can actually prove it also. We have taken that rings, remember? You can actually take a point here. You can say there is a ring, and integrate, and you can do that. There's a better way. Listen to this. Choose any random point anywhere. So if you choose any random point here, we can make an argument like this. So you can take a sphere, something of this sort. Right? So this is called a solid angle. You need not know what it is exactly, but yes, whatever it is, the angle is same. So if this distance is r1 and this distance is r2, so this charge here will be q1 and this charge here will be q2. This q2 is proportional to r2 square and this charge q1 is proportional to r1 square. That much we know. And if you look at the field here, the field is proportional to q by r square. And q is proportional to again r square. So basically both of them will cancel out. So we get E1 is equal to E2 since Q1 by R1 square, right, is equal to Q2 by R2 square. So that ratio, right, they will always cancel out. So the field due to this guy, so the field at a point is proportional to Q by R square. And Q is proportional to R square. So E is constant at a point due to any small piece. So if you take any random point here, so therefore field at point P is 0. Basically, they cancel out. So this is going to give a field E in this direction. And this is going to give a field E in this direction. Again, the proof is not important. I'm just trying to show you like, there, you could have got 0 like this. So I have chosen a random point in the sphere. I have taken a random distances. And I proved that whatever charge was there on this piece would be proportional to that square there. So it would cancel out every time. Is that making sense? So that angle which we got, right, is actually called a solid angle. We don't have in the portion, but later on I will define it a bit for you, but we really don't need it. But anyway, the results are more important for this. We also prove this in another way using Gauss law later on, but for now, let's focus on the results. The potential is kq by capital R. This is constant. It depends on the radius of the shell. And for points outside, it will be kq by small r for r greater than r. So if you try to plot a VR graph, it would be constant and then it drops. These are the results for a hollow shell. Clear? The next shape is a solid sphere. So remember this thing, only for spheres, you can treat them like point charges when you're outside. No other shape behaves like that. So there is a theorem on that also. We will not worry about it. It's called a shell theorem. So for a sphere inside, it is kq small r by r cube. So it increases linearly, r less than equal to r. For points outside, it is kq by r square. Again, behaves like a point charge. So if you put an E versus R graph, it would be a linear function and then it drops. The potential, now again, among the shell and the solid sphere, again, solid sphere ka potential is one of the most important formula. I have seen questions directly being asked on the potential only. The potential inside a solid sphere, kq by 2r cube into 3r square minus small r square. You have to remember this. That formula itself is a question. It means r less than r, and outside is kq by small r. And when you try to plot a graph for this, you have to be careful with the graph. The starting part of the graph. So this is one of the most common mistake. What is the potential at the center? People think it is zero. No, the potential at the center, when you put r is equal to zero, you don't get zero. You get 3kq by 2r. So the graph will start somewhere here, 3kq by 2r, and you can see it is an r square. So it's actually a parabola up to r. After r, it's a 1 by r function, so it decays. So that's how the graph would look, something of that sort. It's an inverted parabola there. Please note down the results. Copy down roughly. You will need these results. Yeah. Once you go outside, every shell becomes like a charge at the center. All copied. Put it on, note it down. First, we'll do one or two problems to get used to the formulas, and then we'll talk about the shell and sphere again. There is a lot more on this. The theory and the problems, yeah, I can call it theory, I can call it problems, everything becomes together. But let's see. Samyak.
अगर वो होलोस्फीयर में अगर R इक्वल टू R में इलेक्ट्रिक फील्ड क्या होगा?
वो undefined है. That's why we don't put that equality there. Meaning either you're inside or you're outside. There is nothing like you can't go and sit on the charge. So it's undefined actually. So we will never take a case R equal to R. It's a discontinuity. Basically graph भी देखो ना, suddenly break हो गया ना. So either you're inside or outside. You can't be on the charge. So yeah.
Sir, if so, then doesn't it like means it makes no sense कि हम inside the solid sphere potential define कर पा रहे हैं
Inside a
क्योंकि
solid
you'll
sphere
always
में
be on a thin shell, right?
in a solid sphere.
Yes, sir. Like
नहीं
you'll
नहीं, see
always be
problem
in
क्या है ना,
the edge
see
of
in a
point.
solid sphere the charges are distributed, right? So even if you go and sit on a charge, that dq tends to zero. But shell में आप क्या कर रहे हो? You're putting a finite charge on a thin surface. You're getting it?
So we can also say in this one dq tends to zero, but
Which one?
in the hollow sphere also at the edge for small area.
Nee, no, see, but thickness is also small. No? It's like, see, the end of the day, there's nothing called a point charge, remember?
Okay.
In reality, there's nothing called a point charge. It doesn't exist only. Everything has some dimensions. It is you and I, we are saying uska dimensions hai hi nahi. So it doesn't work. So we can't go and set on the charge. Here, the dq will tend to zero. When the charge is distributed, right? It is spread out. You can keep very, so you're saying charge is there, but it's a very little amount there.
Okay, sir.
So kind of. All clear with the formulas? So let's do a question to get used to the formulas first. And remember, whatever you're doing, everything repeats exactly same thing in gravitation. We are literally going to, speed run in gravitation. I will just say these are the formulas. We are not going to do things again. There we will do the problems which I couldn't do here. So So Gravy will not take much time. If you're done electro properly and thoroughly, Gravy is like a simpler version of electrostatics. So we have a hollow shell and we have a solid sphere, concentric. So let's say this thing is plus q, radius r. This thing is plus q, radius 2r. Right? So hollow shell, solid sphere. Both are concentric. So we have point O, we have point A, we have point B, we have point C, we have point D, we have point E. So when I say B, right, it is on the surface. So distance between O to A is r by 2, O to B distance is r, O to B 3r by 2, O to D 2r, O to E 5r by 2. There. Basically, we covered every case, in, out, everything. So what I want you to find the field and potential at OA, B, C, D, E. Find the electric field and find the potential at O, A, B, C, D, and D due to both of them. I'll show you one. You just take a minute to observe, and then I'll show you one or two, and then I'll give you time for rest. Mm-hmm. See, I'll just show you what I'm asking you. I want potential and field due to both of them, right? So I will do one at a time. Let's take hollow shell separately. Let's take the solid sphere separately. So the first question you should ask, where is the point? Is it inside or outside? If it is inside, use the inside ka formula. If it is outside, use outside ka formula. So for the first point is EO. Ask yourself, where is O for the shell? Inside or outside? O is inside the shell. What is the field inside the shell? Zero. Where is O for the solid sphere? At the center. What is the field at the center of a solid sphere? Zero. What is the total field? 0 plus 0. Are you clear what I'm asking? What about the potential at the center? Again, where is the point? O is inside the hollow shell. What is the potential for a hollow shell? Look at the formula. KQ by radius. What is the radius of the hollow shell? 2r. Great. Where is O for the solid sphere? At the center. What is the potential at the center? 3KQ by 2r. So basically in this formula, I kept r is equal to 0. Add them, you'll get the answer. Are you clear what I'm asking? So this is how you have to find for each and every point. Can you do for A, B, C, D, E? Try, I'll give you 2 minutes. Then I'll show you for A, B, C. That's it. You just have to ask where is the point? Inside, outside. Put the formula. So this will cover all the cases for hollow shell and solid sphere at the same time. In, out, everything. And if you just add them up, you will get the net resultant. Try. You have written down the formulas, use them, check them, and write it down. That is the best way to remember things. Okay, let's see for A. Check your answers. So EA, where is A? A is inside the hollow shell, so it is still 0. Where is A? It is inside the solid sphere. And what is the formula? K, Q, small r. यहाँ पे small r is r by 2. I will leave it like that by r cube. So you know the formula. The direction is away from the center. Potential at A. Where is A? Inside the hollow shell. What is the potential? KQ by radius. Radius is 2r. What about this thing? Inside the formula is KQ by 2r cube 3r square minus r by 2 whole square. Can you imagine? This thing was a question in mains. Find the potential at r by 2 in a solid sphere. Bas ho gaya. Mains question tha wo. And 99% people left it endgame. So, yep. Why do you think like if you score, you can easily score 80 plus in physics in mains paper? People just don't practice, don't revise the basic stuff. In max, if you score, I think last time someone scored 8 marks and they got some 97.5 percentile in max in a certain paper. So happens a lot. If in max, I think if you score 20 marks, 25 marks, I think you did well. You have to score the rest in physics and chem only. Physics and chem, if you can put to 80s, and max, if you can put some 25. So I think, yeah, 185 or something, that will still put you at 99.405 percentile. Anyway, so that's about A there. What about B? EB? B is on the surface. No, surface for a solid sphere is fine. So it will be for a hollow shell, it is still inside. Uh, yeah, it's a EB, it is still 0. So the solid sphere, it is KQ by R square. Potential at B, this is still inside KQ by 2R. Plus, this thing is on the surface, so KQ by R. Please check your answers.
So can you explain EB wala part
EB, where is B for the hollow shell, inside or outside?
inside?
So 0. Where is B for the solid sphere?
Just outside.
Just outside. So you can use any of the formula. Though both will give you the same answer. It's a
Okay, sir.
continuous function, right? So you can just use KQ by R square. इसलिए देखो ना, इसलिए समय पूछ रहा था. Here I kept an equal to sign, and here I didn't keep an equal to sign. Hollow shell में there is a discontinuity in and out. For a solid sphere, you won't have a problem. The function is continuous. All clear till VB. Any doubts on this? And then let's go ahead with the rest. You keep asking the same question. C, where is C? C is still inside, 0. Solid sphere के लिए it is outside, so it is KQ by 3R by 2 whole square. What about the potential at C? KQ by 2R. This is KQ by 3R by 2. Potential at D. Field at D. Now the shell will come for the first time. KQ by 2R whole square. This also is KQ by 2R whole square. They just behave like point charges at the center now. And VD will be KQ by 2R. If you're outside, your life is easy. You can just replace them with point charges and you're done. So field at E, KQ by 5R by 2 whole square. KQ by 5R by 2 whole square. Potential at E, KQ by 5R by 2, KQ by 5R. All clear with this? Any doubts on this? Clear. Next one. So we have a solid sphere here. made a thin tunnel along the diameter. Uniform charged sphere. The charge is plus q and the radius is r. You are releasing a particle minus q and mass m from rest. C is the center. Find the speed and the time taken to reach the center. There's no gravity, nothing else. It's all electrostatic forces. Find speed and time when it reaches C. We will see more variations of this in gravitation. Okay, speed, Param got something. What about time? Okay, let's see. There are two ways you can do. One is brute force energy, and one you can actually, I'll show you what it is. Simple question. So straightforward, you're falling inside. This is your state one. When you reach the center, you'll have some speed v. This is state two. Since there are no external forces, energy in state one is equal to energy in state two. Energy in state one, initial kinetic energy, 0. Potential energy, what is the potential due to the solid sphere? Kq by r into minus q. This is the potential on the surface due to solid sphere. Remember, that's how you write energy now. Instead of mgh, now we are writing or half kx square or whatever we wrote potential energies. Now we are writing this thing. So potential energy on surface, potential at potential at a point into charge will give you potential energy due to sphere. When you reach the center, the potential becomes 3kq by 2r into minus q, and the kinetic energy is half mv square. Solve this, you will get a v. One step, you're done. Clear? Now, there is a much better way. Now, when you're falling here, let the particle be somewhere here at a distance x. The force acting on the particle will be charge q into E. But what is the field inside? The field inside is kq x, the distance from the center, by r cube. So we can write F is equal to minus ma. So we are taking acceleration in the opposite direction, in the direction of x. So this would be kq small q x by r cube is equal to minus ma. You can clearly see this is an SHM. KQ small q by mr cube into x. This is your omega square. So this thing is oscillating in SHM, and how much it is going from? That's you're starting from rest, so that is your extreme position. Huh? X is equal to r is your extreme. X is equal to 0 is your mean, and you'll go to the other side. X is equal to minus r, that's your other extreme. You want to find the time only from here to here, and how much will that be? T by 4. So time taken to reach A will be T by 4. That's 1/4 of 2 pi by omega. So how to find the speed here? You can find that also. At the center, the speed is maximum. Because that is a mean position. Therefore, what is Vmax? Vmax is A omega. But what is the amplitude here? R omega. So that's your answer. Because you're starting from rest, isn't that the extreme position? So the radius of this sphere is the amplitude of the motion. There you can completely do with this with SHM also. Whichever you like. Energy is also fine. SHM is also fine. All clear with this? Next thing. We have mercury drops. Identical and mercury drops of potential V. Why mercury specifically? They're conducting. Now we'll not go too much into the details. They kind of act like hollow spheres, okay? So we will talk about that in Gauss law. So for now, just treat them like that. We can treat them like hollow shells. Even though they have volume, for some reason the charge stays only on the surface like a hollow shell. So we have n drops of these things of potential V are combined to form one big drop. This is another good means question. Find the potential of the big drop. So we have an identical spherical mercury drops. Each one has a potential. You combine all of them, you got another big sphere. Okay, let's see. So what's the catch here? So when you have n drops, first of all, understand they also must be having some charge. So let the charge be q and let the radius be r. So V is equal to k q by r. So you're finding the potential on the surface. Now when you make this into one big drop, now this big drop will have a charge capital Q, which is n times small q, and the radius is r. We can get the radius r from volume conservation, n into 4 by 3 pi r small cube is equal to 4 by 3 pi capital R cube. So we get r is equal to n to the power of 1 by 3 small r. Therefore, the potential of the big drop will be k capital Q by r. Capital Q is n small q and r is nothing but n power 1 by 3 small r. Most people mess up the charge part. They take the charge also to be same. And this thing turns out to be n to the power of 2 by 3 into v. Clear with this? So in case of a surface tension, only the radius used to change, isn't it? Surface tension used to remain same. But here the charge also will become n times. So you'll get n power 2 by 3. Right, Shreyansh. Right, Samyak. Right, Arya. Got it. All clear with this? The next thing. Now this is an interesting concept. We call it the self-energy. So theory, questions, everything. Now think about this. When you say a shell has a positive charge, aren't the charges of the shell interacting with each other? Every charge on the shell is repelling every charge on the other parts of the shell. So these things are interacting, isn't it? So there will be some energy because of this. Meaning, for some reason, if the shell explodes, all these particles will repel and fly off to infinity with the kinetic energy. So there is some energy stored in the system, right? Because of its own interaction. So that's why we call it self energy. So it is same thing as potential energy. We call it self because it's your own interaction, right? It is like this. When you donate money to an orphanage, you're donating money, right? When you donate it to yourself, it's self donation. So ever did that? Sometimes, people say, right, you should donate some money to poor people and you donate to yourself, right? Kind of. So you're donating, right? You're donating to poor people. So yeah, you are helping poor people in need. So you donate to your own self and it works. So generally it happens on the end of the month when you're in a hostel and your pocket money is yet to come for another 4 days, right? So you run a donation camp for yourself. So you start searching under the bed, under the old pocket to find some 2 or 3 rupee coin for money. It happens a lot in IIT. I think when we're in IIT now, by fourth year, third year, tak na, we got a habit of stopped eating in the mess. Mess ka food was fine, but it is little boring. No spices, no masala, nothing. It's a very healthy food. If you eat that in 3 months, you'll become really healthy. So, but right, we don't want to eat healthy food. We can't eat for so long. So we got a habit of eating late night food like 2 o'clock, 1:30. We used to go out in the restaurant. IIT we used to have restaurants which are open till night 2:30. So we used to get 1:30, 1:45 and eat. Now the problem was at the end of the month, right? We always used to become a little short of money. I think it was still 2 days for the first. I used to get my scholarship on first of the month, 1,000 rupees. My friends used to get a hell lot of pocket money. That's a different story. They used to spend everything in a week and used to become beggars. So one day what happened, right? I and my friend were there. He came to me and said, Arun, bahar jaake khat hai na? I said, yaar, where is the money? Plan is good, but I don't think we have any money left. We finished it. So we have to wait for 2 more days. He said, let's do one thing. I'll go to my room and search everywhere. You go to room, you search everywhere. Let's see how much we can find. I said, theek hai. He went, he searched old clothes, that, this. I also went and searched. He came and said, how much you got? I said, I got 1 rupee. Right? I found 1 rupee somewhere under the bed. He got 2 rupees. So total we found 3 rupees together. That is the kind of beggars we are getting it. कुछ भी नहीं बचा था. That ATM card had zero. मतलब if it was allowed to go to negative, I would have borrowed it, but it's a debit card. So 3 rupees we had. Mess ka food is there. We can go and eat. You won't die. You'll have enough all the facilities there. Then I told him, see, chup chap mess jayenge, we'll eat and come. Right? Let's not do any nonsense. He said, you wait. I will figure out something. I said, theek hai, go. After half an hour, he comes with 40 rupees. He says, chal, abhi jate hain. 40 rupees is a big amount of money. Matlab, you can get 2 biryanis with that. And they said, us time biryani 20 rupees mein milta tha. Acha wala. So, and I was like, how did you get it? I said, chalna. I figured it out. I said, theek hai. We both started going. And then around 12 o'clock, some of my friends came and they started knocking my door. I went and I said, what? And happy birthday, Arun, happy birthday, Arun. I said, like, what? I said, like, what? I said, it's your birthday, right? I said, okay, maybe. I'm not sure exactly. I was confused. He's like, oh, sab theek hai. Where is the cake? I said, who said it is my birthday? I said, Arvind hai na, wo bola tha tera birthday hai. I said, I said, go ask him, right? I don't know it is my birthday. I myself didn't know that. So what this idiot did, he went to everyone and said, अरे कल अरुण का बर्थडे है, सब रेडी है, बस 2 rupees मिसिंग है, राइट? केक के लिए 2 रुपए मिसिंग है. He went to the next guy, said the same story. Like that, he begged 2 rupees from 20 people, and he got 40 rupees. And we ate biryani with that. That guy is looking at me, I'm looking at him. All these people, and in look, देखो ना, these people are also smart, huh? They thought, chalo, I'll contribute 2 rupees, then 12 o'clock I can go and get a cake, right? Because I gave 2 rupees, I can go and get a cake now. I deserve it. It is my right to go and get a cake ka slice. So these idiots also came greedily to eat that cake. 20 people, right? For 40 rupees ka cake. So, so here everyone is greedy there, okay? That's it. They started beating me and him right and left. We started running. They caught me and him. Right? They call bumps, na? Yeah, then, 4 people catch your hands and legs like this and then punching your bum. So they kicked there with the legs and everything. For me, they just kicked with my legs. For Arvind, though, they took hockey sticks and started punching his ass. So right and left, they started beating him. सब बिरयानी digest हो गया. So that is how we used to do. Hostels are fun, right? I mean, you should definitely be with friends in a hostel. You will get to learn a lot of things. Anyway, so what is the self energy? So we can define it like this. This is the amount of energy required to assemble a system by bringing individual charges from infinity. So let's see how it works. So let's find the self energy for hollow shell. Look at the definition. You want to construct a hollow shell by bringing little charges from infinity. So this dotted line is the place where I want to create a hollow shell. So initially there was no charge. So we have a radius r and there is initially no charge. Great. Now what you did, you started bringing dq charge from infinity. You brought this charge and you started spreading it on the surface. Think of like this, you're just sprinkling it. When you did that, the shell started getting some charge. So you got some plus q charge, radius r. Right? And you continued this. You started bringing more and more charge and you're sprinkling it, sprinkling it, sprinkling it. Eventually, it becomes a shell plus q and radius r. So you have created a shell of this thing. You're getting the process? You're bringing dq, dq, dq. But now think about this. When you're bringing dq, the potential at infinity is 0. Now, when you bring already plus q charge here, when you're bringing this dq, you think this plus q will keep quiet? The plus q is already sitting there, will repel the dq which is coming. So the potential on the surface will be k small q by r. So that means as you put more and more charge on the shell, you'll get more and more repulsion. So you have to put more and more work. So the small change in work done, the small work done will be q into the potential difference. That's dq into potential difference will be v surface minus v infinity. I can simply say du basically, because anyway change in kinetic energy is 0. So this is your self energy. So this is all the energy that is required to assemble this. This would be integral dq, v surface will be kq by r. Limits will go from 0 to capital Q. You end up with kq square by 2r. That's your self energy of an hollow shell. That means if the shell explodes into small pieces and when they fly away, the kinetic energy of all these pieces will be kq square by 2r. So a self-energy of a hollow shell. So this much energy you can extract when this thing explodes is kq square by 2r. Should definitely remember this. Exam, you won't have time to derive this. All clear what we did? Now, using the same logic, can you find the self-energy for a solid sphere? Now, the derivations are important because tomorrow they will change something else. They will say it is a sphere whose density is equal to rho naught r. So, variable density. And then if you don't know how to integrate, you can't do it. Can you try for self-energy for a solid sphere? So it's a question and a theory. I showed you for a hollow shell. How will you construct a solid sphere? Think for a minute, then I'll show you how it works, and then I'll give another 2 minutes. First thing, how will you even start? Idea is the same. Initially, you have nothing. You bring dq charge and you create a sphere. Find the self energy of a solid sphere, uniformly charged solid sphere. Anyone not convinced with, not clear with this self energy thing, please ask. Anything that you're not clear, not sure, anything you're confused. Okay, let's see. I'll show you how it is constructed, then you try. So, solid sphere. So initially you have nothing. Then you created a solid sphere of charge plus q and radius r. So charge is also changing, radius also changing. And when you bring dq charge from infinity to here, you're spreading it over the surface. And in this process, you're also increasing the thickness. So dq is spread over the surface, increasing the thickness by dr. So you can actually write like this. So q will be rho into 4 by 3 pi r cube. So dq will be rho into 4 by 3 pi r square dr. What is rho? Rho is nothing but total charge by 4 by 3 pi r cube because it's a uniform density. And when you do this, eventually you'll create a full sphere of charge plus q and radius r. So the story is still the same. So potential at infinity is 0. Potential on the surface is k small q by r. What is small q? This. What is dq? This. And you have to integrate. Got the difference? In case of a hollow shell, the radius was never changing. You're always keeping it on the surface only. You're compressing the charge on the surface. Here, you're keeping the density uniform. You're increasing the thickness continuously. That's the difference. So in an exam, they will change this rho ka value. They'll say rho is equal to rho naught r. You still know how to integrate. The process is important. नहीं होता डिनोमिनेटर में 2 नहीं आएगा हाँ आर्य
Sir, will we always get like require the same energy for constructing a system in whichever way we do?
हाँ it doesn't matter. This is like a state function, right? So सोचो ना, when you say potential energy between 2 points k q1 q2 by r, does it matter how you have brought them to that particular distance?
No.
Conservative forces na basically. So it does
Okay.
not depend on the path. You bring one dq first and everything. इसमें क्या है ना, if I bring it like this, I can calculate it because I can find the potential. But if you say like this, first I'll put the charge here, then I'll put it here. Problem इसमें क्या होगा? I can't find the potential on the surface. So the argument is this: if you can find the energy in this case, it should be the same in every case because the forces are conservative. So what will be the self energy here when you integrate? Integral dq into v surface minus v infinity. So dq will be rho 4 by 3 pi r square dr. Surface will be kq, that is again rho 4 by 3 pi r cube by r, limits from 0 to r. And when you solve this and substitute q ka value, right, I remember the answer, I'll write it down. The U self energy should be 3kq square by 5r. You have to substitute rho back in terms of q. That's your self energy for a solid sphere. Right, Afsa. You get exact same results in gravitation. K का place में G आएगा, Q का place में M आएगा. So there we are not going to derive again. There we will just put the result and say it is similar one. All clear with this? Yeah, let's see one question on this. We have two conducting shells. Let the radius be r and let the radius be 2r. They're connected by a wire. They're very far. And we have a switch here. This guy has a charge minus q and this guy has a charge plus 2q. When you close the switch, find the final charges and find the heat produced. These are conducting shells. Do you guys remember in the beginning of the chapter I told you, if two conductors are connected, what happens? The charge will transfer till the potential becomes same. They're very far so that you don't want them to interact with each other. And they're connected by a conducting wire. This is another good mains level question. If they just ask you the potential at the mains level question, if they ask you heat produced, it becomes a little higher. When switch is closed, find final charges and heat produced. Let's finish off. Last one for the day.
So the spheres are solid or hollow?
Hollow conducting shells.
Okay.
Whenever you connect two things, you always get a potential becomes same. That's the main idea there. Okay, let's see the first charge part. So how do you handle these kind of things? Okay, Samyak got something. So this is how I would prefer to do. Okay, you can say final charges are Q1, Q2, and you can do, but I would say this way is better. Let charge small q flow from here to here. Because sometimes they'll ask a question like this: how much charge flowed through the switch? So then it'll help. So then if q went from here, then how much charge will remain here? You will remain with 2q minus small q. Then how much charge will be here? Minus q plus q. Agreed? Charge has to be conserved. What is the potential of this shell? K q minus capital Q by R. What is the potential of this shell? K 2q minus q by 2R. Since they're connected by the wire, V1 is equal to V2. So we end up with Q minus Q is equal to 2Q minus small q by 2R. 2. So that would be 2Q minus capital 2Q is equal to 2Q minus Q is equal to Q is equal to 4Q by 3. Be careful, this is the charge that flowed. So if you substitute this thing here, this will become 2Q by 3 and this will become Q by 3. That's your final charges. So how much charge went through the switch? 4 capital Q by 3. Is the process clear? So assume Q went from one to another side, the charge conservation. Find the potential individual and equate them. All clear with this? Now, how do you get the heat produced? Now, if you look at the shells initially, and if you look at the shells finally, so initially the charges were minus Q, 2Q. Now the charges are Q by 3 and 2Q by 3. So what changed? Self-energy. So the initial energy of the system is K minus Q whole square. So be careful, self-energy doesn't care about the charge. KQ square by 2R. This will be K 2Q ka whole square by 2 times the radius, which is 2R. U final is K, the radius ka charge ka square, Q by 3 ka square, 2R, plus K 2Q by 3 whole square by 2 times 2R. That's your self-energy. The heat produced will be the initial energy minus final energy. The difference is the heat produced. Always, whenever charge flows from one place to another place, simple question. Why does charge flow from one place to another place? Because that's more stable, right? Every system in the universe will do something to become more stable. That means you are going to go to a lower energy state. That means the difference energy has to go somewhere. So if the charge flows, you'll always get a heat. That's one way to think. Another way to think of like this is this. Listen, the moment you close the switch, won't the electrons rush with some speed? They just don't go slowly, right? They go with a speed. So when they go so fast and hit the conductor here, what happens to all that kinetic energy? It becomes heat. Getting it? You can think of like that also. But all clear with the steps? So that's a bit about self-energy there. So next class when we catch up, we'll continue with this solid sphere and everything. We still have more varieties on this, right? So we'll see that part, and then I think by next Thursday we should be able to wrap up the chapter. After that, we'll start off with gravitation. So we have almost done 29 questions there. So please make sure to go through the notes, right, and start solving. If you have not started already, I think it's time you should start doing it. Okay, with that, we'll wrap up for that. I'll see you guys again next Tuesday, same time. So any doubts, anything else, please stay back and ask, or else you're free to leave. I hope everyone saw the